calculating illumination levels at elevated points is possible using various methods and tools. Lighting simulation software, such as DIA-Lux or AGA32, can generate illumination calculations and provide detailed lux values at any specified point in a space. It is also possible to calculate illumination levels at elevated points manually using specific formulas and principles. One common method is the inverse square law, which states that the illumination level decreases in proportion to the square of the distance from the light source. For guidance on how to perform lighting calculations, refer to the IES Lighting Handbook by the Illuminating Engineering Society and the Handbook of Applied Photometry by AC Lighting Incorporated. Considering the difference in illumination between a 250 watts HPS lamp mounted at 50 feet and a 400 watts metal halide lamp mounted at 25 feet, the illumination level at a point depends on several factors. Firstly, light output in lumens is a key consideration. A 400 watts metal halide lamp typically produces more lumens than a 250 watts HPS lamp. Secondly, mounting height plays a significant role. The higher the mounting height, the lower the illumination level at ground level. Thirdly, luminaire efficiency matters. The efficiency of the luminaire, such as its optics and reflector, affects how effectively light is distributed. Finally, ambient light such as natural daylight or other ambient light sources can affect the overall illumination level. Based on these factors, a 400 watts metal halide lamp mounted at 25 feet typically provides higher illumination levels than a 250 watts HPS lamp mounted at 50 feet. However, the specific difference in illumination will depend on the specific luminaires and lighting conditions used. To delve deeper into manual calculations, let's explore the inverse square law in more detail. The inverse square law is a fundamental principle in photometry stating that the illuminance at a point is inversely proportional to the square of the distance from the light source. Mathematically, this can be expressed as E equals I divided by D squared, where E represents luminance in lux or foot candles, I represents the luminous intensity in candelas, and D represents the distance from the light source in meters or feet. This law holds true when the light source can be approximated as a point source and the light rays strike the surface perpendicularly. When calculating illumination at an elevated point, you need to determine the distance between the light source and the point of interest. This might involve using the Pythagorean theorem if the point is not directly below the light source. For example, if a light is mounted 20 feet above the ground and you want to calculate the illuminance at a point 15 feet horizontally away from the base of the pole and 10 feet above the ground, you would first calculate the straight line distance from the light to the point. This distance, d, would be the square root of the quantity 15 squared plus the quantity 10 squared, which equals approximately 18.3 feet. You would then use this distance in the inverse square law formula to find the illuminance at that point. It is important to note that the inverse square law assumes that the light rays are striking the surface perpendicularly. If the surface is angled relative to the light source, a correction factor must be applied. This correction factor involves the cosine of the angle of incidence, which is the angle between the light ray and the normal or perpendicular to the surface. The formula then becomes E equals I times the cosine of theta divided by d squared, where theta is the angle of incidence. Now let's discuss the software tools mentioned earlier, DIA-Lux and AGA32, in more detail. These are powerful lighting simulation programs widely used by lighting designers and engineers to predict illumination levels in various environments. DIA-Lux is a free software that allows users to create detailed 3D models of spaces, import luminaire data from manufacturers' catalogs, and perform sophisticated lighting calculations. It can generate visualizations of the lighting scheme showing illuminance levels, luminance distributions, and glare ratings. AGA32 is a more advanced commercial software that offers similar capabilities but with additional features, such as daylighting analysis, energy calculations, and advanced rendering options. When using these software tools, you would typically start by creating a 3D model of the space, including the dimensions of the room or site, the reflectance of the surfaces, and the placement of any obstructions. Then, you would import the luminaire data, which includes the luminous intensity distribution curves, or IES files, for the chosen light fixtures. These IES files describe how the light is emitted from the luminaire in all directions. The software then uses this data to perform ray tracing calculations, simulating how light travels through the space and interacts with the surfaces. The result is a detailed map of illuminance levels at any point in the space, allowing you to evaluate the lighting design and make adjustments as needed. Regarding the IES Lighting Handbook, it is considered the authoritative reference on lighting design and engineering. Published by the Illuminati Engineering Society, it covers a wide range of topics, including lighting terminology, light sources, luminaires, photometry, calculation methods, and lighting applications. It also provides recommendations for illumination levels for various tasks and environments based on research and best practices. The Handbook of Applied Photometry by AC Lighting Incorporated is another useful resource, particularly for understanding the practical aspects of photometry and lighting measurements. It covers topics such as light meters, calibration procedures, and measurement techniques. Returning to the comparison between 250 watts HBS and 400 watts metal halide lamps, let's consider the spectral differences between these two light sources. HBS lamps emit a yellowish light, with a relatively narrow spectrum concentrated in the yellow-orange region. This can result in poor color rendering, making it difficult to distinguish between colors accurately. Metal halide lamps, on the other hand, emit a whiter light with a broader spectrum, providing better color rendering. This makes them more suitable for applications where color discrimination is important. However, metal halide lamps typically have a shorter lifespan and are more expensive than HBS lamps. In addition to the wattage and mounting height, the choice between HBS and metal halide lamps depends on the specific application requirements, considering factors such as color rendering, energy efficiency, lifespan, and cost. The efficacy of a lamp, measured in lumens per watt, is another important consideration. This indicates how efficiently the lamp converts electrical power into light. Metal halide lamps generally have higher efficacy than HBS lamps, meaning they produce more light per watt. However, HBS lamps have improved in recent years, and some high-efficiency HBS lamps can rival the efficacy of metal halide lamps. Also important is the light distribution pattern of the luminaire. This describes how the light is spread out across the area being illuminated. Different luminaires have different distribution patterns, ranging from narrow spotlights to wide floodlights. The choice of distribution pattern depends on the shape and size of the area to be lit, as well as the desired uniformity of illumination. For example, a narrow distribution pattern might be suitable for accent lighting or highlighting a specific object, while a wide distribution pattern might be better for general area lighting. When evaluating a lighting design, it is important to consider not only the illuminance levels but also the uniformity of illumination. Uniformity refers to how evenly the light is distributed across the surface. Poor uniformity can result in dark spots and glare, which can be uncomfortable and reduce visibility. The uniformity ratio is typically defined as the ratio of the minimum illuminance to the average illuminance. A higher uniformity ratio indicates more even lighting. In addition to illuminance and uniformity, glare is another important factor to consider. Glare is the excessive brightness that can cause discomfort and reduce visibility. There are two types of glare: disability glare, which reduces visibility, and discomfort glare, which causes discomfort. Glare can be caused by direct light sources, such as exposed lamps, or by reflected light from shiny surfaces. To minimize glare, it is important to choose luminaires with appropriate shielding and to avoid placing light sources in the direct line of sight. Using matte or diffuse surfaces can also help to reduce reflected glare. Finally, it is important to consider the energy efficiency of the lighting system. Lighting can account for a significant portion of a building's energy consumption, so it is important to choose energy-efficient light sources and luminaires. LED lighting is becoming increasingly popular due to its high efficacy, long lifespan, and good color rendering. Using lighting controls, such as dimmers and occupancy sensors, can also help to reduce energy consumption by adjusting the light levels based on the time of day and the occupancy of the space. In summary, calculating illumination levels at elevated points requires considering various factors, including the light output of the lamp, the mounting height, the luminaire efficiency, and the angle of incidence. Software tools such as DIA Lux and Agith32 can be used to perform detailed lighting calculations and generate visualizations of the lighting scheme. The IES Lighting Handbook is an authoritative reference on lighting design and engineering, providing guidance on calculation methods and recommended illumination levels. When choosing between different light sources such as HBS and metal halide lamps, it is important to consider the specific application requirements, taking into account factors such as color rendering, energy efficiency, lifespan, and cost. By carefully considering these factors, it is possible to design a lighting system that provides adequate illumination, minimizes glare, and conserves energy. Remember that consulting with a qualified lighting designer or engineer can provide valuable expertise and ensure that the lighting system meets the specific needs of the application. Lighting design is a complex field, and there are many factors to consider to achieve optimal results.